Hello everybody, thank you so much for having me. My name's Amanda and I'm a first year PhD student at Edgehill University. And this presentation is the results of my master's dissertation, which I completed last year at Lancaster with Dave, Hugh and Kako, looking at the petrogenesis of high silica rhyolites within Iceland. First, I'll introduce what we actually mean by the term high silica rhyolites. And these are deposits that, on a dry basis, contain over 75% weight of silica, so they put over here on the far side of the TAS. They're one of the more evolved magmas and form at temperatures of around 800 to 900 degrees at shallow depths and at pressures at around 300 megapascals. It's interesting to note here that there have been studies that show a relationship between the amount of silica within a deposit and the pressure of formation. So for example, here we have 77 and 78 weight percent forming at around 100 to 200 megapascals in comparison to 74 weight percent, which can form up to a gigapascal. The question here is, how do we have these magmas in Iceland where the typical eruptive deposit is a basalt? To model this, we use the petrography and whole rock geochemistry, coupled with the knowledge of the structure of the Icelandic crust, to inform on geochemical modelling using rhyolite melts of various starting compositions. And from this, we were able to get the petrogenesis. The deposits. We report on 4 isolated deposits here from across Iceland, ranging from 75% weight silica up to 77% weight silica on a dry basis. And it's worth noting here that within Iceland you have rift zones, which are shown in pink, and they are the surface expression of the Mid-Atlantic Ridge, where partial melting is thought to dominate, and flank zones, which are shown in orange, where material is derived from the Icelandic plume and fractional crystallization is thought to dominate. And because here we have the high silica rhyolites occurring in both rift and flank zones, so Sultrafell down here is in the flank zone, it means we are likely having a common process operating across both volcanic environments. Within thin sections, high silica rhyolites are predominantly hyaline, with no more than around 8% of crystals. These are mostly plagioclases, specifically andesine and clinopyroxene. So the image here, you can see that the glassy ground mass exhibits flow banding, often distorting around larger crystals, and any microlites within this tend to do the same. The right image here shows a crystal of allanite and zircon, which was found in one of the samples. And this is particularly interesting as allanite is a carrier of light rare earth elements and is typically found in metamorphosed deposits or as an end-member phase in intrusive intermediate rocks. The fact that in the majority of samples the crystals appear broken suggests that they are xenocrystic, and the presence of allanite in particular may indicate the involvement of an intermediate body in some way. In terms of major elements, other than all having commonly high silica, there are no commonalities amongst the deposits, and when compared with normal rhyolites, they show no linear trends. However, within trace element geochemistry, there are far more commonalities, and the deposits tend to cluster together. So for example, zirconium here, they tend to cluster at around 2 to 400 parts per million. And these values are particularly important as they show that the high silica rhyolites contain far lower concentrations of incompatible elements than you would expect from their evolved nature. Again, in particular zirconium, you can see here that they typically exhibit range as shown by basalts at around the 200 parts per million zone. And this indicates that our source rock for these rhyolites must be primitive and depleted in incompatibles. Knowing that the source rock must be primitive, we first looked at the structure of the oceanic crust and, on a thicker scale, the Icelandic crust. And you can see here we have these large layers of gabbro, which are derived from the depleted mantle and thus are depleted in incompatible elements. And these represent an ideal starting composition for modelling. So using rhyolite melts, we fractionally crystallised 3 gabbros, and the results are shown here. You can see that all 3 of them failed to reach the 75% weight silica mark, and in fact silica actually begins to decrease at around 73%, which marks the onset of quartz crystallization and depletes the melt in silica. However, the ternary indicates here that this process actually produces a tonalite composition, also known as plagiogranite, when the volume of normative quartz exceeds 20%. It's well known within the literature that within oceanic crust sequences, you get pockets of plagiogranites or occurring as thin layers amongst the gabbro, and they're formed as a result of extreme fractional crystallization of a gabbro. For Iceland in particular, the partial melting of plagiogranites was theorised to be the source of rhyolites within Iceland. However, this theory was dismissed because the volume of rhyolites in Iceland is simply too large to be produced solely from plagiogranite melting. However, this doesn't really apply to high silica rhyolites as their volume is substantially lower. Using rhyolite melts, we partially melted 4 plagiogranite compositions, 3 of which were derived from the extreme fractional crystallization of the gabbro, which you saw earlier, and 1 of which was taken from a published geochemical analysis of a plagiogranite within Iceland. These all produced a high silica rhyolite from around 10 to 20% partial melting, and they all accurately reproduce the silica value, some even reaching up to 88% silica, and this is likely from the partial melting of quartz and plagioclase within the plagiogranite. For the trace elements, a batch model melting was used, and again, these all accurately reproduce the high silica rhyolite values, and you can see that the high silica rhyolites and the model values all tend to cluster together, so zirconium, they're all between 2 to 450 parts per million. Here we have the full petrogenetic model. We start off with a gabbroite melt derived from the mantle and depleted in trace elements. And this stores in the crust, cools, and undergoes fractional crystallization to form a pocket of intermediate plagiogranite where minerals such as an allanite may form. We then have an intrusion of rising melt, either derived from the plume or the rift, depending on where you are in Iceland. And this partially melts the plagiogranite, and particularly the quartz and plagioclase phases, to form a small amount of high silica rhyolite melt. And these are very dry magmas, and due to their silica percentage, they are also very viscous and will likely entrain crystals such as the allanite and plagioclases from its surroundings as it rises up through the crust. These are then erupted and are likely quickly cooled to form a glassy xenocrystic high silica rhyolite deposits that we see in Iceland today. Thank you so much for listening. I'll happily take any questions.